Okay. Well, sorry with everyone, we'll get started, and thank you for filling up the room. This is really cool. So I'm Kevin, you just saw me at the other session, and I work with Paul and Vicky on the Mac, and Haley Drennan as well, who runs our website. And if the feedback gets really bad, just let me know. But thanks to email from Brandy about XBTs, we've kind of brought in the discussion to sound speed issues in general for multi-beam mapping, and this is something that we think about a lot with the Mac, usually in the context of pushing for more profiling and getting pushback from ships, not just in the fleet, but all the ships we work with about why we can't do more profiles. And so it's always a discussion about what are the trade-offs of how your systems are set up, what it costs to operate them, the environmental impacts, and then what it means for the data. So on our wiki, we have, we made this one page, top 10 multi-beam issues. If you had only 3 minutes to go think about multi-beam stuff, you can go to this page and think about your top 10 common issues that keep coming back up and up and up. And you can see we have a water line down at the bottom, perpetual issue. But then number 2 is inadequate sound speed profiling. So this is a major topic for us. And on the wiki specifically, we're seeking feedback from users across the fleet. Anybody with experience doing sound speed profiles, you're welcome to contribute. Wanted to just back up a little bit here. So none of the talk today is meant to be authoritative about anything. It's really meant to have a conversation about what is working, what's not working for the ships. But I wanted to start with a beautiful sunset. A little bit of recap on why we care about sound speed. So one of the coolest resources that I've come across is this theory of operations document from Signal, and it's old school. Really, the way it's presented is really neat. You can go through and follow from first principles how a multi-beam works, and just these images from that black and white manual are pretty helpful. So I did rely on that. It's linked on the wiki. And this is meant to recap from like a really fundamental standpoint why we care about sound speed. So I think we're all familiar with seeing smiles and frowns in the data as we drive along, or having other refraction issues. But really thinking about how a multi-beam works is where I wanted to start. So if you're starting with one element, propagating some waves, you start putting elements together, you get constructive and destructive interference. That is the foundation of every other process downstream that the multi-beam does, from beam forming to beam steering, all of the yaw stabilization, roll stabilization, pitch stabilization. Every single process that the multi-beam is doing behind the scenes depends on these couple little factors. And one is the element spacing, one is the sound speed, and then of course, if you know that sound speed and that spacing, and you know what frequency you're using, you can do all the geometry to make sure that the wave fronts are interfering the way you want them to. And as you add elements, that's how you achieve a narrower beam width in the far field. So you can go back to this document, the theory of operations, and you can step through that whole process. It's totally fascinating. And as you work your way up to hundreds of elements, which is what these deep water systems have, then you can see how important sound speed becomes in that factor. So as an example here, we're looking at measured transmit power level, basically in the long shift direction. And this is an experiment from RV Sally Ride. And this is just to show you in the real world, this is an example of what that radiated sound field looks like in a very narrow slice long shift. And if you go from -80 to +60 or 80 degrees, you see you have a couple spikes in the middle. I have a laser pointer here. So this is kind of the main lobe here, and your power levels are up at 220 dB or higher, and you're achieving a very narrow beam width. So all of that power is concentrated. That's only possible because of all of those factors: the spacing of the elements, the known frequencies, and then the sound speed at the transducer phase. So once you are forming a beam, you want to maybe steer it somewhere to achieve some sort of stabilization. And that depends also on those same couple parameters. We'll just move ahead. When you do that in the transmit and receive directions, you cross the beam patterns in what's called a Mills cross. This is an example of the gondola on Valcor 2. They have a half-degree EM124 transmit array. It's absolutely massive. And then a smaller RX array that's oriented 90 degrees to that. And so each of those systems is achieving a certain beam pattern, one in transmit, one in receive. You cross those and you get a single narrow beam. And every single bit of beam forming, of beam steering, is happening for each of those beams. So in some cases with the new EM systems, you have over 1,000 of these beam products in each slot. And then sometimes you have a dual slot system. So you're talking, this is happening 2,000 times per beam cycle. And the net result is the surface sound speed to start is critical for all of that beam forming and that beam steering. That enables all of the stabilization processes during transit and during receive. And then that's only at the array. That's the starting point for all of the refraction correction downtime. So you start looking at your profile. Thought this was really interesting. We're all kind of familiar with Snell's law and how you can track array through different layers of sound speed. And in this case, I thought it was fascinating that we call it Snell's law, but it was actually discovered like 700 years earlier by this Persian scientist, and they don't get enough credit. But the point here is that once we achieve the launch angles, there's a whole other process that goes after that. That's the ray tracing through the different layers based on your sound speed profile. Where that sounding ends up in terms of tracing and calculating your range along that ray path depends completely on your sound speed profile. There is no really other information for the sonar to use. So again, this is an example of why I like the wording of this document. When they're discussing the range calculation, eventually you're just going to run out of time, yielding the total range to that sounding total cumulative travel time through all those layers. So I'd highly recommend checking out that document on Wiki and just getting a deeper dive into the appreciation for why sound speed is that important. Beyond all the stabilization and ray tracing processes, there's a lot of interest now in backscatter products, and to make good backscatter products, you need good absorption data. So that's another reason that sound speed profiling is very important. But it's beyond sound speed; it's also salinity and some other information. So just to recap the profile real quick, all of the range calculation depends on the cumulative travel time. The backup, that depends on launch angles into the water column, and continuing along that ray path. Every bit of that refraction correction depends on the validity of that profile for what the sonar is trying to calculate. So that's the recap. What we wanted to get into is just an overview of common setups and trade-offs. And again, this is to have another discussion, so you can stop at any time and we'll talk about it. Generally speaking, there tend to be two types of setups. One is a flow-through system, where that would be important for especially ships with ice windows, where you can't really put a sound speed probe in a meaningful way through the hull. You might have to build your sound speed at the surface sensor into a flow-through system. The other is preferable, where you have your in situ sensors directly next to the arrays. And so anything that the sensor is picking up, you could assume is the reality in the front of the array. So there are some pros and cons to each of these. I mean, with a flow-through system, you can generally maintain the sensors themselves a little bit more easily. You don't need divers necessarily. The downside is the conditions that the sensor is picking up on may not represent what's at the array. And we just talked about how critical that is for everything the Multibeam is trying to do. There's also potentially some latencies and other issues, especially if you're cutting through gradients or turbulence near the surface. For the in situ arrays, you're pretty much guaranteed to be representing what the arrays are really facing. It's a standard for shallow water systems where you are working in more dynamic environments, and there's almost never a height or time difference between what the sensor is picking up and the arrays are experiencing. But there are issues, and we'll get to some of the feedback from the survey about biofouling and the difficulty of access to those in situ arrays. On the flow-through system specifically, and this is not to pick on Sekuliak here, but if you are transiting through an area of stratified water, you may be picking up on very different water masses in your flow-through system compared to what your arrays are seeing. So in this case, imagine Sekuliak's picking up the high sound speed water on top, but the arrays are seeing something with a lower sound speed. That's going to just throw everything off for every step of the process. Beam steering, refraction correction, and finally your range calculations and your depth.
Didn't do it. Sorry.
And that's in a simple case. Imagine you're transiting through some of this EK data on the right that we picked up in the Arctic, where it's just extraordinarily dynamic. You have almost no hope of giving the multi-beam the data that it really needs in time. Quick overview here of all the different options, or the most common options for sound speed profiling. We broke this into expendable and reusable columns because that is kind of a starting point for this discussion in the RV Tech email list. And then, of course, there are other considerations like whether you can remain underway. Do you have to stop the ship? What does that mean for your operations and your cost of operations? The cost of each sound speed profile. Is that going to mean that you're going to maybe turn off the multi-beam because you don't really have time to take a profile? There's a whole bunch of other considerations here that you're probably all much more familiar with than I am, but I think the general classification of expendable versus reusable is going to become more important over time. And specifically with XBTs, I came across this paper about comparing the fall rates, which is an assumed fall rate, and finding some not trivial differences depending on where the probes are manufactured, and that was interesting. Okay, on to our sound speed survey and all the feedback we got from the fleet. We heard from 19 ships, including the Titanic. Thanks, Paul. And most of you have transport systems, not surprisingly. And it was cool to hear back from some fisheries vessels that use ME-70s, and then some of the ships that have SPP-29s. So those are multi-beam systems, but we don't always think of them as multi-beam mapping systems. So there's a good cross-section of what's installed in the fleet. Most of them are not behind ice windows. Makes sense. Most of the ships use a time of flight sensor for the surface. We can call it the transducer sound speed value, because surface is, hopefully your transducer is not at the surface, because then you're hanging in air. That's terrible. Couple snarky bits of feedback here, probably from Charlie Wilkins, where you could just set it at 1500 meters per second and hope for the best, and that's the worst idea for topics. Thankfully, he said he's just looking at it. And then the other question for the surface sensor here is how close is the sensor to the arrays? I mean, what assumptions can we make about how representative that really is for what the arrays are seeing in real time? If you're in a perfectly mixed upper layer and the mixed layer is 20 meters deep, your draft is 10 meters or less, and you probably don't care if you're in the middle of the ocean and you're experiencing the exact same water at the intake or the sensor versus what the arrays are experiencing. But in coastal waters, that's going to be maybe not the case. Or if you're in the Arctic and you're transiting through eddies, I think I have a screenshot of that, of the wildly different upper stratified water layers that you can transit through. So we wanted to know how close are the sensors to the arrays, and it's variable. Not surprisingly, most ships have Reason SVP-70s. I think a lot of these responses are biased from the NOAA survey launches with their EM-2040s, and if I'm not mistaken, Jackie sell them frequently with the Reason probes. So those are very popular surface probe. Of course, the Belfort and the AMLs as well. And then for flow-through systems, the Seabird systems are de facto standard there. We wanted to know if there were backup sensors available, and in most cases, yes. And in most cases, it's a flow-through. So lots of TSGs in a flow through system, and that's just from the max perspective, that's really nice to hear that, that there's a backup. So you can still collect data if your surface sensor failed. Do you have any specific concerns or challenges? Marine growth, I've just taken screenshots of some representative answers here, and marine growth was a problem. Access was always a problem. Yeah, distance, yep. Location, yep. So pretty similar set of concerns across the responses there. This was really interesting to me in terms of where is your sensor in relation to the transducers. And I realized I wasn't very specific about height differences or along ship or across ship differences. I just wanted to know roughly how far away is your sensor. And you can see here we span from less than a meter to 26 meters and 30 meters and maybe unknown, just far away. That was interesting because even if you have an in situ sensor, it's not a flow through. If it's not close to the arrays, there might be a little bit of an issue there. And then, well, I guess this depends on how fast you're going in terms of how that would impact the multi-beam data. But we wanted to know, do you have a sense of how long it takes the water in a flow-through system to get from the intake to your sensor? And it's anywhere from a few seconds to over 10 minutes. So that will have various variable impacts on your mapping. 10 minutes might be okay if you're in a totally mixed upper layer. That might be totally fine. 5 seconds would probably be preferable in most places, so that if you do get into more variable water, you're representing that quickly for the multi-beam. And then a bunch of responses indicated that they just weren't really sure. So that might be an interesting test. I actually don't know how you would test it, but you could probably estimate it just by looking at your flow rates and your pipe diameters and all that. If anybody has any feedback or suggestions on how they measured that, it'd be cool to share that. We wanted to know if beyond the timing. Oh,
I was just going to say, I think, and maybe there's a flow through best practices, but I think you can like introduce some like red dye at where the intake is, and then basically just time it to when you see it in your piping system. I don't know if there's any other ideas out there.
Yeah, thank you. For the audience at home, Kristen is recommending introducing red dye at your intake and seeing when it shows up. So that's a great idea. For flow through temperatures here, aside from the timing lag that might be present and how that would impact you if you're transiting through variable surface layers, there could be an actual temperature difference between where you bring in the water and where you sense the water. And if there's no difference, it's probably okay. But if there is, it'd be really cool to know what that is and think about what that could do for your multi-beam data. If you are familiar with CIS, it'll typically warn you if you have a difference of, say, 3 meters per second between your surface value and your profile value at that transducer depth. But if you're looking at a 1 degree change in water temperature, that's almost 5 meters per second for most seawater. And CIS would be giving you red lights at that point. So it's something to consider. Most of the answers were less than half a degree, and they've actually been measured. And it probably depends on the temperature of the water mass that you're in and other operations on board. If somebody's got the air conditioning on in a certain space, but that was good to know that most of the responses indicated they had measured it and it was less than half a degree. There were a few that were 1 to 2 degrees, depending on what water mass you're in. And then getting into the profiling responses. So most people use XBT, it's not surprising. And most ships have a CTE, although that doesn't mean it's used all the time for mapping. Some ships with ROVs have the CTE on the ROV. We've talked with a couple of vessels about planning their overnight mapping to use the CTE profile from the ROV upon recovery. And that's been helpful in terms of reducing XBT use. Very few moving vessel profilers or underweight CPDs out there. And of course, not surprisingly, XBTs are the most frequently used profiling methods for mapping, for routine mapping. Yeah, no Nansen bottles. The interval, this is another question that we run into in our work with other ships in the NOAA fleet for other exploration vessels. Everybody wants to know how often you do a profile, and I don't know. Depends. Depends. Fortunately, most of the people kind of agreed. It depends. It depends on what you have for expectations from the user group. What's the water mass like? What kind of indications are you getting about how variable it is? And we'll get into some software tools that might help answer that question. For deep water mapping, it seems like most of the ships are about every 12 hours. And depending on your schedule there, if it's one at midnight and one at noon, you'll be capturing kind of the extremes of the daily heating and cooling, and that might be good enough. Very few ships are doing every 4 hours or less. I did one survey on the Blake Plateau, and we were doing every 45 minutes for weeks. It was awful. So if you use XBTs, most people are using deep blues, not surprising. I didn't think to make this multiple choice, but yeah, it's all Certifican probes, and most of the deeper versions, so not surprising. We were happy to see SoundSpeed managers very widely installed and appreciated. This person said, yes, we love it with a little heart. That's great. And we are also very happy that we get to work with Giuseppe, and he's turning out new versions of this as quickly as possible. So if you do have issues, I know this came up in the previous session, email Giuseppe. There should be a link directly in SoundSpeed Manager. You can submit your concerns and export the error log so that you can troubleshoot very quickly. General feedback on the profiling system. Most people would rather not litter the seabed, but there aren't many alternatives in terms of being quick and cheap and good enough for mapping usually. So yeah, I can't say any of the feedback surprising. It was just nice to hear it. Sorry.
Yeah. So when you talk about the MVP being expensive, what are you talking ballpark? I don't have no concept.
Yeah, I can't. I don't know. I'm guessing close to 6 figures. That's a guess, though. Lee, did you have any? Okay.
Just that they're challenging to maintain.
Yes.
It's expensive not only in the upfront cost, but also it's not.
Yeah, and just, I mean, qualitatively, we've been on ships where they have 2 identical underway CTV systems. One worked beautifully. The other one has been visited many times by the manufacturer, and if you're lucky, you get a bird's nest back, and if you're unlucky, you lose the probe again. So we've had highly variable experiences with those at sea. I'm sure you have as well. Their concerns, let's see, yeah, trapping stuff in the water, fishing gear, biofouling, and stuff like that. And then for ships that have either gondolas or retractable systems, there are questions, for instance, with the new RCRVs. Each multi-beam has to have its own surface sensor because one's on a drop keel, one's on a hull. So there are some considerations there too. And we have some slides from Colleen Peters, who presented a special session on some SIS updates at the meeting in Edinburgh a couple weeks ago. And she was nice enough to share the slides that specifically had to do with sound speed updates. And so these are adapted from her slide. And the recommendation there is she wanted to remind the audience that Sound Speed Manager is wonderful, but you can also always use the SVP editor directly in the software. And it's very flexible. It's getting better all the time. You can create filters to bring in all sorts of formats from your sensors directly. You don't have to use Sound Speed Manager if you don't want to. There are other reasons that we really like Sound Speed Manager, but just be aware of that direct option.
Dan Fornari online has a comment he'd like to ask. Can you hear us, Dan? If so, go ahead and unmute. Where'd he go? He moved. There he is. Oh.
Okay, how about now? Can you hear me all right?
Talking to the microphone, asking on you.
Hey, Dan, this is Kevin. Can you unmute? You might be able to hear you.
I thought that I have unmuted myself.
I see his microphone moving, but I don't hear him. He was
I
quiet
have,
earlier too, wasn't
I have unmuted myself.
All right, we'll check back in, Dan. If you hear you, we'll stop. So in SIS, there's also a Warlord Atlas setup. You don't have to use sound to manage directly for that. You can just bring in the Warlord Atlas data and SIS will handle that. In terms of some specifics here about how SIS handles different inputs, Colleen strongly recommends using SSP datagrams instead of the ASVP files. And that's because you can preserve data that's important for absorption coefficients for each frequency. So you can just export an ASVP file from lots of different software and send it that way. But if you can get set up to transmit SSP datagrams, you'll actually be preserving more data all the way through the chain into the KML output or DAL. Maybe it's only SIS5, so KML. And that's really useful later on processing. There is a quick guide SSP that's available locally on your SIS machine. And in there, there's some kind of handy little tips about how to set up your SSP datagrams. And we've been on chips where for some reason the sonar just all of a sudden is rejecting sound speed datagrams coming across. And what I liked about this quick guide is it breaks down the types of errors that it'll pick up on and say, in this case, SIS will try to reformat the datagram and get what it needs out of that. In other cases, you have to fix what you're giving to SIS, and then it will work. So I like this because I think we've had a couple cases where the sonar just says, yep, no depth received, can't do any of the receive process, and it's because it's missing something really fundamental about the sound speed profile. Even in some cases where it might have been earlier versions of Sound Speed Manager where you went over 1,000 points of the profile and SIS said, oh, can't use that, but we didn't know why. And here it is in the guide, so I just want to point that out. Final notes from Colleen here. Again, transmitting to SIS from Sound Speed Manager is good. It reserves all the fields. If you export to ASVP, you lose the absorption data. And in both of those paths, you use the file name of the profile. This is a question that I think Kongsberg and some of the software providers are working on, so that you could preserve the file name all the way through, which is specifically for processing down the line. That's not reality yet. And then some other tips here. So if you are using Sound Speed Manager, as of this version, there are some defaults that are set up. You have to go into your SIS setup and enable a couple of things for that to work. Colleen is pushing hard to release new versions of SIS pretty quickly with a lot of really good updates. So make sure you update. Speaking of updates, Sound Speed Manager, we'll just go through some of Giuseppe's slides here. And for those of you who aren't familiar, this is why we recommend it. It's open source, free, 5,000 downloads since it was introduced. Well, everything's showing up here, but it's meant to help you manage all of your sound speed data during a cruise and after, and give you a database that you can hand to anybody handling the data later. Oh, Giuseppe has animation in here. That's nice. So yeah, it really does streamline the workflow, and the whole idea of this software is that it's flexible. You can set up your own sets of buttons and auto process methods there. It's very flexible, and if you need something specific from Giuseppe, just email him, and he and his buddies will get on it. What we like about it is very flexible, so you can bring in stuff from all sorts of sensors and export to lots of different formats. And then, of course, you can use Warlord Atlas or other databases to extend the profiles and bring in historic data. If your profile cut out at 760 meters, you can go all the way down to what Kongsberg expects using better data than simply a straight line. During acquisition, we have a couple of things that Giuseppe wanted to highlight. There's the survey data monitor, and this is getting back into, okay, how's our sound speed at the surface looking? What is the multibeam expecting, and what's the impact on the data as we transit through some funky waters here? And Sound Speed Manager has this mode where it'll keep track of these things and plot it out in time, so you can kind of see, are we in a stable water mass, or is this jumping around? And then it'll try to make recommendations for you on when to do new profiles. You can set up certain parameters around, okay, well, I can't do them every 4 hours, but I can do them every 8 to 16. Tell me when I need to do another one, or should I wait? Should I hold on to that XPT and try to minimize waste? So you can set up some parameters there, and it will help you out. That might be really helpful on transits as well. Speaking of transit mapping, there's server mode. If you can't do any profiles, this is not a replacement for profiles at all. It's just not. But it's a worst case backup if you're transiting and you don't have any options to do profiles. You can set up SoundSpeed Manager to send World Ocean Atlas or RTOFs or some other databases. It will track where you are, and when you get into a new node for historic data, it'll send the appropriate estimate of what that SoundSpeed environment would be at that time of year and ship it over to SIS. So it's better than nothing, for sure. We also, from the Mac side of things, have caught a few issues with multi-beam setup using SoundSpeed Manager, which was very unexpected. But I was on a ship where this little green cross here, which shows the, see my mouse? Yeah. So if you look at where the green lines cross, that's supposed to be the surface sound speed value and the array depth. And that's all in real time. That's compensating for heave and everything like that, and your waterline offset. And when you look at that and you realize it's not reporting what we think the array depths are, we dug into that, and it turns out there's a big waterline issue. So very unexpectedly, SoundSpeed Manager helped us find a sign convention error that was a 4-meter waterline issue. So just fun other things to think about, other applications here. And then when you're done collecting the data, you can actually look at what the impacts might have been on your swath quality and your depth biases based on different profiles in the database. So you can compare one to another directly. If you are running multiple systems like EKs or sub-bottom profilers or USBL, and you want a better estimate of your sound speed for those applications, it's really nice when your EK matches your multi-beam depth. It just feels better if those depths match up. You can do that by getting a harmonic mean sound speed from your most recent profile or any profile in the database. You can just, I asked Giuseppe if we could get harmonic mean out of some profiles we had, and he said, oh yeah, that feature was implemented 5 years ago. And it's true, you can just get the harmonic mean and then plug that into your EKs or your other systems, and it will improve the range calculations there. That might be really useful if you're looking at certain targets like seeps or other midwater features, and you're trying to measure, say, how high up in the water column did something actually go. Oh, we talked about synthetic profile server not being a replacement for XPTs. We do have some other resources on the wiki. This is some work that Vicky did with her team, looking at variability, in this case on the Blake Plateau. And again, getting back to the idea that collecting the data, even if it has rough sound speed information in it, is still worthwhile. We can try to correct that after the fact. And in this case, you can, if you do have a lot of profiles and you're correcting the data still, because it's the edge of the Gulf Stream, you can use that as a proxy for other oceanographic takeaways. Vicky, do you have anything else you want to add?
Just that in this case, every effort was made to get the sound speed correct, and it still wasn't sufficient by our standards in terms of fit for purposeness in an integrated bathymetry synthesis, even though the errors met IHO specifications. So there's a lot that we can do in post-processing to fix things. And again, just echoing Kevin's statement for me earlier, always good to collect data. This happens a lot during transit data because you don't have the adjacent lines as context, but it even happens during service.
Yep, this was like one profile every hour and it still was not.
Yeah,
not good.
really very.
So speaking of planning your surveys and that sound speed variability, another tool out of the HydroOffice framework is called SmartMap. And this is meant to be a nice web interface to help you look at the forecast for sound speed variability anywhere in the world, depending on certain models. The long-term goal here is to help the surveyor think about the timing of those profiles to make better use of ship time and hopefully not litter so many XPPs. So zooming out here, we're just looking at the Pacific Ocean. It's pretty benign. If you zoom into Hawaii, in this case, you can't actually pick too many different models, but there are some other models such as the Gulf of Maine, very high resolution. And again, things look okay today, but you can step through up to 5 or 6 days and see how that's going to change. So if you are planning some really important survey, you might look at, is there going to be some eddy from the Gulf Stream coming by on Tuesday, and maybe not be in the middle of that. So for instance, yeah, the East Coast here. And the way this is color scaled is just, I think the idea is to show you what would be the expected impact on your multi-beam data, your depth errors, if you were not doing adequate profiling for that environment. So we'll get to the last topic here, environmental impacts that we have not been able to solve for or predict. And this is an example from one of the UNL ships where we had a couple of years ago some concerns about the heading sensor and how that was affecting the swath, the distribution of soundings in the along track direction, but also wobbles, to put it lightly, on the outer swath. And that was all addressed through some updates over the last couple of years. And this system has a new EM124, seems to be working well. But last winter, there were some artifacts on the East Pacific Rise in an area where historically we had not seen wobbles. So it raised a lot of questions about what's going on here. And we did a full checkout. We compared it to historic data from that vessel, looked at all the sound speed information. You can see, might be hard to see here, but the gray and the blue profiles, there's quite a bit of difference in the mixed layer depth there. And here's what some of those wobbles look like on the outer swath. 10 to 15 meter periodic artifacts in the outer swath in 3,100 meters of water. That was during one of our roll calibrations while we were trying to check out the whole system. And then you go to another site for another part of that calibration and there's no artifact. You're a little bit baffled by that. The whole system checked out on all the calibration, the geometry review, noise testing, all those things. And finally, we thought, there's a growing interest in, or awareness at least, in some of the oceanographic conditions that are variable, specifically internal waves. This is an issue that shallow water mappers are highly aware of, but we hadn't always thought about it in the deep water. And we asked the ship to do a little octagon with 10 minutes or 15 minutes of data on each of 8 headings. And the swath changed fundamentally on each of those headings. With all of the other attitude time series remaining the same, surface sound speed stayed consistent. So the only thing changing here was heading, and I think it's heading or orientation with respect to some internal wave field. So you think about crossing internal waves in one direction, it would have a certain impact on the swath. Cross it 45 degrees or 90 degrees off, and it would have a very different impact on the swath. And we think we saw that. This is deep water, almost 3,000 meters. The best case was 5 meter ripples on the outer swath, which is really manageable. Worst case was 50 meter wobbles, and nothing changed except orientation with respect to potentially this internal wave field. We dug a little bit deeper, talked to some of the more expert folks on this, and they said, oh yeah, that area is well known for internal waves. It doesn't mean that that is definitely what happened there, but we checked everything else out the best we could. And it raised some questions about what's the impact of the flow through TSG on the system, or is that a factor in take depth or temperature change? So that ship is going to be making some changes to their surface sound speed setup and hoping that that's not the cause, which means we might still be dealing with environmental issues that we just can't solve, unfortunately. But future work, there is interest in tracking these things. There are other systems on board like the EK80s. And if you're experiencing those kinds of wobbles, we didn't think of it in the moment, unfortunately, but you can turn on your EK80s, sync them up with the casing and see if you are observing these internal waves or at least highly stratified water layers that are changing depth in time. And you might even change the ship course a little bit and see if that changes its frequency. there is effort to improve the EK80 tracking method so that you can pick up on those mixed layer depths and track it in real time, and then maybe feed that. I think this is down the road, but you could feed that to the multi-beam and say, I don't know what the actual sound speed profile is out here, but I could take your most recent profile and then adjust the mixed layer depth to what I'm seeing right now with the EK80. And in this case, they compared some data we collected in the Arctic, and they had a 95% success rate tracking the same mixed layer depth with the EK as they found with the CTD when the mixed layer depth or mixed layer was present. So I think that's promising. It's not a total solution there, but it's a step in the right direction and could eventually reduce the number of profiles that we have to do. I think that's it. So just want to open it up. Now we're running a little late already, but
Got 5 minutes, I think. Right? You know, you got 5 minutes?
yeah.
You got a lot of talk on the chat. Let me put this over here so you can catch up with everything that's going on.
This is Dan Fernari. Can you hear me okay now?
Hear you.
Gabe, can you hear me all right?
Yes.
Yep, we can hear you.
So I just really wanted to say I appreciate very much these presentations that were made and the detail in which you've gone into this. I really feel like it's a pretty critical part of getting a system that will work well in a variety of environments. And sound speed is critical, but I also think with these new systems that surface sound speed and decreasing any latency when the system gets that number or series of numbers is crucial, because we did experience some serious sort of artifacts with the system on Atlantis earlier this year. And although the jury is still out, in my opinion, I do think that it has to do with the lack of adequate either data update rates or the lack of resolution of the sound speed sensor, the surface sound speed sensor. So I'm grateful that Mac is looking into this and that other folks are paying attention to it. And one of the comments I made is that it seems to me that the people who are paying the bills, the Navy and NSF, that they should not allow operators to buy these systems without making sure that they've actually figured out how to put the best sound speed sensor into the system.
Yeah, thank you, Dan. And thanks for pushing for this so hard. I know that was a very frustrating time. But yeah, we appreciate your effort on this.
And yours as well. Thanks so much. Yeah, I mean, I'm hopeful that we'll solve it. But I do think that it is a challenge and it is something that folks need to be aware of, both users, science users. And that's why I really supported Kevin and the Mac's efforts to try to get as much information as possible from all operators to know exactly how they're dealing with this issue and whether they've had similar issues, and so that when folks go out to do surveys, they are well aware of it and can figure out how to best accommodate.
On that note, kind of for folks who are taking surface sound velocity from a TSG and a closure, are most people correcting for the temperature change with a hold temp or an intake temp? And if so, is that an easy thing to integrate, or is that kind of a one-off in a series of equations and a complex process?
Yeah, I don't know. So the question for the online audience is there any compensation being done for the flow through TSGs based on like a known temperature difference in the pipe? And I don't know. Does anybody do that here?
Most ships have a remote temperature sensor at the intake.
Okay.
And that's usually the reported temperature, and then the conductivity is calculated in the 45 later, where it doesn't matter if the temperature is changed.
Yeah.
I guess I'm wondering what that process looks like. Is that built into the acquisition system where you do that calculation, or is there an off-the-shelf product that you can use to do that?
Yes, Seabird has an off-the-shelf kit that you can add on, and it's also necessary for PCO2 measurements. So that's another reason to have it. And then we've also had some engineers that done an offset too without made measurements in the lab what the loss is for some systems.
Yeah.
But the direct read are definitely sensors are way to go if you can get it on the ship.
Well, I think we're there. I think we're at 50 minutes here.
Thanks for showing up, and email us or check out the wiki. We're always looking for contributors to that. If you have specific things you want to share, we'd love to see that.